Ocean surface waves carry terrifying mass and momentum. For coastal communities and offshore infrastructure, they represent an immediate physical threat. For decades, marine forecasting indexed wave danger using significant wave height, a single scalar measurement. The assumption was that predicting the hazard meant predicting how tall the water would get before it reached the shore. But an ocean state is a vector field. To calculate the force approaching a coastline, forecasters must track peak period, which measures the time between successive crests, and the precise angles of wave direction. The National Weather Service is currently transitioning away from these pure scalar models. Today, forecasters are beginning to map the exact trajectories of multiple coexisting wave groups to improve operational safety. Building a seawall to withstand a specific height is ineffective if the model ignores the velocity and the angle of the incoming energy. Protecting coastlines depends on predicting where the force is coming from, not just how tall it is when it breaks. To study how these wave vectors intersect across a global scale, the Atlantic Ocean Basin serves as a laboratory for intersecting hemispheric energy. This map visualizes 44 years of ERA5 reanalysis data. By segmenting the basin into 5 strict latitudinal sectors, we can isolate the unique wave climates operating within each zone. The Northern Hemisphere sectors are defined by high seasonal volatility. Landmass constraints and steep thermal gradients cause wave heights to swing violently between winter storm peaks and summer lulls. The Southern Hemisphere is the opposite. Because the westerlies here have an unobstructed fetch, these sectors hold the highest mean wave energy on the planet. But at the center, the tropical Atlantic appears suspiciously stable. The seasonal variance in wave height is statistically flat compared to the poles. This stability is a mathematical illusion produced by looking only at wave height. The tropics act as a collision zone for the entire planet's ocean energy, masking complex physical intersections under seemingly calm surface heights. To find the hidden complexity, we have to look past height and analyze the peak period probabilities within the tropical Atlantic. This is a probability density histogram for tropical wave periods. A localized single-source climate produces one peak, but this data shows a clear double-humped bimodal signature. The first distinct peak occurs at the 8.1 second mark. The second peak occurs independently at 12.1 seconds. This bimodal signature indicates that the wave energy in the tropics is fragmented and originates from separate physical events. The 8.1 second peak is the fingerprint of long-period swells generated by remote extratropical storms in the Northern Hemisphere. The 12.1 second peak identifies swells arriving from the Southern Hemisphere's storm tracks. Finding this specific data signature in a single geographic zone confirms that the tropics absorb wave energy migrating from opposite ends of the Earth. Mapped onto the ocean, we track long-period northern and southern swells migrating toward the equator. Overlaying the final variable reveals localized short-period wind seas generated by equatorial trade winds. This intersection of north, south, and local energy is the Trimodal regime. This regime creates a specific obstacle for coastal modeling. Forecasters cannot rely on a single dominant source when energy arrives from 3 distinct trajectories simultaneously. Accurate forecasting for a tropical beach requires tracking the decay of storm systems currently raging thousands of miles away in the polar regions. To understand how these migrations are steered, we have to look at the atmospheric drivers governing the entire basin. The primary driver is the North Atlantic Oscillation, or NAO, a massive pressure differential between the Icelandic low and the Azores high. A positive phase in the NAO intensifies pressure gradients, which increases local surface wind speeds at high latitudes. Data shows that the NAO holds a strong correlation with significant wave height in the North Atlantic, with an R² of 0.81. But how does an atmospheric pressure anomaly near the Arctic physically manipulate the wave climate down at the equator? The statistical breakthrough is that the NAO does not alter the height of tropical waves. It alters their mean direction. The NAO dictates 74% of the interannual variance in the direction tropical swells are traveling. Large-scale climate oscillations act as a remote control for the ocean, steering wave vectors across the globe rather than just increasing their size. We can visualize the geometry of this shift in the vector field between 40 degrees west and 20 degrees west. Track a long-period swell vector originating in the North Atlantic as it propagates 3,000 kilometers south. When we apply the precise 10-degree directional deviation triggered by an NAO phase shift, the trajectory changes. Over a journey of 3,000 kilometers, that 10-degree shift forces the wave energy to strike land 500 kilometers laterally from its original target. This 500-kilometer displacement completely changes the erosion patterns and port safety conditions for the affected coastline. A minor atmospheric pressure shift in the Arctic dictates exactly which tropical communities will face destructive long-period energy weeks later. Looking at the entire Atlantic basin reveals a web of climate indices, the NAO, the SAM, the Arctic Oscillation, all shifting wave angles simultaneously. Decadal data shows and peak period across the world's oceans. Planning only for taller waves will fail as these teleconnection-driven directional biases intensify. Coastal engineers must fully incorporate remote directional teleconnections into their hazard matrices to account for where the energy is being steered. Modern physical oceanography maps the global vector fields that steer water, rather than relying on the simple measurement of surface height.